In this problem, I need to verify the identity. And so I'll start with one side of the equation and transform it into the other side of the equation. In this particular one, I'm going to start with the left side because it's a fraction, and so there's more potential to kind of squish that down into what we have on the right-hand side. So on the left, I have 1 plus cosine x all over 1 minus cosine x. And what I'll do is say that this is equal to, and now I'm going to work my changes on the right-hand side. So I have 1 plus cosine x over 1 minus cosine x. It's just what we have on the left. And I'm going to multiply both the top and bottom by the conjugate of either the top or the bottom. And in this particular case, I'm going to go with the conjugate of the bottom. And you can try either one and see what works best. And what will likely happen is that possibly either one will work eventually. It's just a matter of getting more experience with this and seeing what you want to do. So what I'm looking at here is when I multiply by 1 plus cosine x in both the top and bottom, then when I multiply these two factors together, this is a difference of 2 squares, so it's going to wind up being 1 minus cosine squared x, and I can turn that into a sine squared x. And I'd rather have the denominator be one term rather than the numerator, because then I can break up into separate terms if I want to and see if I can do some simplifying. So now that we have this, I'm going to multiply. Now I'm actually going to leave the numerator factored. So I'm going to leave that as 1 plus cosine x quantity squared. And the reason for this is because I have an expression here squared. So I'm always keeping in mind what is it that I have, what is my goal, and I'm trying to get something that looks like this. And this looks kind of like that, right? Two terms added together and then the whole thing squared. So I just need to change what I have inside of here. All right. And then when I multiply on the bottom, as I said, I have 1 minus cosine squared x. Now in the next step, I'm going to bring down that 1 plus cosine x quantity squared. And 1 minus cosine squared x is sine squared x. So now I have something in the numerator squared and something in the denominator squared, and I can use my rule of exponents to make this just one big fraction, 1 plus cosine x all over sine x, and then this whole fraction squared. And so normally in algebra, you go in reverse. You'll take something like this, and you'll distribute the exponent to the top and to the bottom. So we're just working that backwards. And now I can separate my fraction into two fractions. So I have 1 over sine x plus cosine x over sine x. And probably at this point you can really see how you're going to get to the end, but you still have to show all the steps. So the steps are really the whole point of the exercise. So you can't skip steps in a proof of an identity. And then we have 1 over sine x, which is cosecant x, plus cosine over sine gives me cotangent of x, and that's squared. And now we are at the end of our proof. Now for this identity, I need to show that the sine of 180 degrees minus theta is always equal to sine of theta. So it doesn't matter what angle theta is, the sine of an angle is always equal to the supplement of that, the sine of the supplement of that angle. All right, so I'm going to start with the left-hand side because it's more complicated than the right-hand side. And so I have the sine of 180 degrees minus theta equals, and now I can use the difference of two angles formula for sine. So it's the sine of 180 degrees times the cosine of theta minus sine of theta times the cosine of 180 degrees. So pretty straightforward there. Now I can evaluate the sine of 180 degrees and the cosine of 180 degrees. So the sine of 180 degrees is 0. So I have 0 times cosine theta, which is good. That means the cosine theta is going away. We didn't want it anyway. And then I have minus sine theta times, and the cosine of 180 degrees is a negative 1. So in my next step, it all gets wrapped up. 0 times cosine is just 0, and a negative sine theta times negative 1 gives me sine theta. And that's the end of that proof. Now for this identity, I'm going to start with cosine of 3 theta and transform it into what we have on the right-hand side. So how do I decide this? Well, I know that I can do something with cosine 3 theta because I can look at this as the cosine of 2 theta plus another theta, and then I can use my sum of two angles formula with cosine. But if I was trying to take the right-hand side and somehow combine it together to make a cosine 3 theta formula, I don't have a formula for cosine 3 theta, so I wouldn't be able to get it to something that was going to then say, okay, so then that's equal to cosine 3 theta. So that's how I know how to start. So I have cosine of 3 theta, and this equals the cosine of the quantity 2 theta plus theta. And then I can rewrite this as cosine of 2 theta times the cosine of theta by itself minus sine of 2 theta times the sine of theta by itself. So remember, when it's cosine and we're adding two angles, A and B, then if it's plus, then we have a minus in our formula. It's just the reverse. Okay. Now, I have cosine 2 theta, and I have 3 formulas for cosine 2 theta. I have 3 different ways of writing that. So I look to what my goal is, and my goal only has cosine in it. There's no sine function there. So I'm going to rewrite this using 2 cosine squared theta minus 1. So instead of cosine 2 theta, I have 2 cosine squared theta minus 1. And that's multiplied by the cosine theta minus, now I need to look at my sine 2 theta formula, and I only have one of those, so that's 2 sine theta cosine theta. No choices there. It's nice because then you don't have to worry about what you're choosing. And then that's multiplied by sine theta. And now I can do some algebra, distribute the cosine theta. So I get 2 cosine cubed theta, which is very nice because we have a cosine cubed theta in our ending formula, or our goal, minus cosine theta. And then this is minus 2 sine squared theta times cosine theta. So because I have 2 sine theta cosine theta times another sine theta in the second term there. I can combine those sine thetas together. This is all just multiplied together, so it's commutative. I'll multiply the sines together and get sine squared. Now again, I don't want to have any sine in my final answer, so my next move, I'm going to bring down 2 cosine cubed theta minus cosine theta, and then minus 2, but instead of writing sine squared theta, this part is going to change. I'm going to change it into 1 minus cosine squared theta times cosine theta. All right. And so then I have 2 cosine cubed theta minus cosine theta minus, and you might want to take an extra step and just rewrite this as 2 cosine theta times 1 minus cosine squared theta. It's a little jarring to try to distribute a factor from both sides into the parentheses at the same time. And then I have 2 cosine cubed theta minus cosine theta minus 2 cosine theta, and then plus 2 cosine cubed theta. So now I can combine like terms. I have 2 cosine cubed theta, and then I have a plus 2 cosine cubed theta. So those add and make 4 cosine cubed theta. And a minus cosine theta minus 2 cosine theta gives me minus 3 cosine theta. And that was my goal, and that is another one proved.